Boom. Hello and welcome back to Calculus 3 for one last time. I know, right? Time flies when you're having fun. So, the last section function and arithmetic to solve the problem rather than integrate the line integral. Today, we are going to take a look again at the basic line integrals, and then if those line integrals are over the smooth curves that are closed, you will be able to use this theorem called Greens Theorem to transform the line integral, which could take a very long time to solve, into a very basic area integral, double integral from either 13.1, 13.2, or 13.3, depending on what you get. So let's take a look at these ideas. So unfortunately, in interest of time, because we are a little bit short on time, I'll have to skip some detailed explanations and go directly into the two formulas and explain it from there, rather than deriving them. So we are going to start with the circulation form. So let C be a simple closed piecewise smooth curve oriented counterclockwise that encloses a connected and simply connected region R. So assume vector field F, standard, right, Fg, where F and G have a continuous first partial derivatives. In R. Then, and here is the formula. I will explain all of this mess, just I have to write it first. All right. So we have field where we can calculate circulation. So circulation is not zero on this field. Start there. Actually, before I go, let me just make clear what this symbol means. You haven't seen this before. You have seen the line integral in the past denoted this way, the integral over the curve C. Well, now we add this piece which says all of this, simple, closed, a closed piecewise smooth curve oriented counterclockwise. That's what it means. It's a closed curve. So you see that little circle over the integral means that it's a closed circle, and then has the connected and simply connected region inside. We know that you can't have islands and stuff that we had in the previous section if you looked at it at all. So that's the notation. Don't let that scare you, and by all means use it to scare others. You have my permission, but you shouldn't be intimidated by this notation. Okay, so it's just a regular line integral that we know from our section 14.2. Just the curve is closed and has the other specs that are up there in a theorem. Line integral, right? So you might be freaked out by the fact that we are putting the equal sign in between a single integral and a double integral. Also, please don't get alarmed there, because you have derivatives within, so one of the integrals gets knocked off by those derivatives, and technically you have a single integral equals single integral, so that's that. Also, the other thing that you can take in account is that the line integral calculates the area of the curtain, right? And that's on this side. This is also the area integral on the other side. So it makes sense in all aspects. So this is one of those theorems that it's a great convenience for us. Can we solve every integral without Greens theorem? And the answer is yes, except some integrals are going to take 30-40 minutes, where for this thing is going to be 2 or 3 lines. So this is going to be used to, for instance, let's say you have a square or a rectangle. So how many sides would it have? 4, right? Square or rectangle will have 4 sides. That means you would have to do 4 separate line integrals and add them all, right, to calculate the line integral around that curve. Now, how hard is to set up a double integral over a rectangular region? Right? You get 0 to 2 and 0 to 5, let's say, and you're done, right? It takes a one line to integrate that thing. So instead of doing 4 separate integrals and adding them all up, you get to do 1 double integral and be done in 2 lines. So this is a huge convenience thing. Do you need it to survive? No, you don't. It's just, very efficient way of computing certain things. So this is the line integral that you can compute from using your previous knowledge, and now we are learning the Greens theorem, which is setting it equal to something that is far easier to compute. Now, does this work all the time? Answer is hell no, right? You have to have non-zero in circulation. That's number 1. Number 2, you have to have the precisely conditions satisfied, which is there has to be a closed curve. So you can solve the problem that we had on a linear line from 0, 0 to 5, 5. That's not a closed curve, and it doesn't, right? It doesn't bound the region. So you can't set up a double integral if it's not bounding a region from all sides. So that's that part. Let's take a look at a quick calculation for this, and then we are going to deal. Oh, by the way, the name of this is two-dimensional curl. Circulation, curling, right? So that's that part. Circulation of a rotation field. Again, do we know that there is the maximum circulation for the rotation field? Yes, right? Radial field has 0 circulation. Rotational field has maximum circulation. We did that in one of our previous lectures. So we're going to take a look now at the example. So we're going to take the rotational field negative y x. So and we're going to look at that on the unit disk, x squared plus y squared less equal than 1, right? So we want to show, so we've seen from before, we know from before that the answer should be 2 pi because we did this calculation in class. But now let's use the Greens theorem and see if we can do it faster. What I have here is that this, using colors, so this is your F, this is your G, right? And this is your R. So now you have, we are going to use the setup is going to be equal to the double integral on partial g partial x minus partial f partial y dA. Now I'm going to point with the arrow here and say whatever witchcraft works for double integrals, you will set it up in that realm. So you have 13.1, 13.2, and 13.3 for polar coordinates. So one of those three will work for this thing. So now let's see. I have a unit circle, so I hope that the polar coordinates make sense to do here. But before I set anything up, I just want to get my dg dx. So let's calculate the curl of vector field f, which is partial g of x. So partial g of x is 1 minus, and then partial f of y is -1, so we get 2. So we will be integrating 2. Now I need to set up a double integral of 2 dA. So what should I use? Well, common sense should tell me that I should use polar coordinates for this one because I'm integrating over the disk. You don't want the square root of 1 minus x squared in your limits of integration and then cranking trig sub, right, forever. You want a very simple integral 2r dr d theta, where r goes from 0 to 1 because the radius in the unit circle is 0 to 1, and you are taking the entire circle 0 to 2 pi. So when you solve this, you just get 2 pi, and I'll just put the arrow here and do the standard. You enjoy this at home. All right. So that's that part, and we have another part. What if you get a radial field, right? If you get a radial field, your circulation is 0, so curl will give you 0, and the whole thing is pointless, right? So we should have another form of Greens theorem, which is the flux form, and we do have it, right? So now we're going to take a look at the flux form. And that one has the same specs. So let's see, be a simple closed, all the same as above, okay? So I can put that, so I can put this, all right? So all the same as above. Then, and I just write the formula here. So we are dotting this with the normal vector, if you remember any of these things parametricized, right, on the arc length, to get our form of f dy minus g dx, which gives me now the double integral of df dx plus dg dy dA over region R, and region R is what you enclose. Again, the same specs as before. You have area equals area, or you can say, okay, single integral equals single integral once one of the integrals cancels with the derivatives that are in the formula. And n is the outward unit normal vector, which you know how to piece inside is called divergence, two-dimensional divergence. So this piece over here is a 2D divergence. And a good example for this would be to calculate the radial field, right? Because radial field is the one that we have. Outward flux of the radial field. So, well, for this example, let's go the radial field. For the radial field, F xy, so the stuff is shining out on unit disk x squared plus y squared less equal than 1. I mean equal to 1. It circles the area. All right, that's what we have. And now we do the same thing. So I have the line C is the circle, right? It's a disk, so it's smooth, right? Differentiable everywhere. It is closed, and it is enclosing the simple as connected and simply connected region. So that's that part. And then I'm just going to put over here that we have f dot n ds is going to be equal to this double integral of divergence. So we are going to calculate divergence first on the side, and then we will decide which kind of chapter 13 integral we are going to set up. So you always have the choice between the three sections. So divergence of f will be, does it kind of make sense to call it divergence? Right, for the radial, right? It shines out stuff. What's happening with any two vectors that are going to, right? They're going to go apart eventually, right? From each other. Stuff is moving away from the source, so it just, the name is so, makes so much sense. So what do I have? Partial derivative of f of x is 1 plus another 1, it's 2 again. And we know that we are supposed to, again, expect 2 pi like we calculated before. So now I'm setting up the integral of 2, and since I'm on the unit disk, better use polar coordinates again. We are on 0 to 1 for radius and 0 to 2 pi for the full circle that we are going. So we are going to 2 pi, and here, just, you know, when you go home, you just do that. So to outline another problem, you could have let's say radial f on a square, right? Radial n on a square that is let's say 0 0 2 0 2 2. Let's do the rectangle so it's clearer. 0 0 3 0 3 2 and 0 2. So if you have a rectangle like this, well, that's your region R, and then you will set your double integral, and then you would have over here whatever the divergence gives you. So I'll just say divergence of f, and then you will do your dy dx. So y's would go from 0 to 2, and x's will go from 0 to 3. So this was a 13.1, right? Both examples we had before were in polar coordinates. I'm just sketching out a problem where you can have this right situation. Now, why am I sketching this? Because if you want to do the line integral, go ahead. You just have a line integral here. You compute that one, and then restart for this, and restart for that, and restart for that. So you have to do 4 integrals in this case. For the Greens theorem, just going to set up this one thing. You calculate the divergence, whatever the field is given to you, and you go from that point. So that's all, right? Try a few exercises. You have the homework open as well to practice, and just do as many exercises as you can, and that's that. Yay, bye.